Hello dear students, in this video I'll be teaching about rational numbers. So let's look at the definition and set notation. So rational numbers are represented by the set of q such that q is equal to p by small q, where p and q are elements of the set of z, that is the set of integers, and q is not equal to 0. So p and q both belong to the set of integers. Now why q cannot be equal to 0? Why the denominator cannot be equal to 0? Because division by 0 is undefined in mathematics, as 0 cannot split any quantity. Now in the standard form of rational numbers, there should not be any other common factor except 1. Okay, so for example, in this problem, minus 12 by 18 will divide the numerator and the denominator by the HCF, which is 6, and we'll get the standard form, which is minus 2 by 3. Now let's look at the family tree of rational numbers. So the rational numbers have the form p by q, and q is not equal to 0. So they include the integers, the fractions, the terminating decimals, and the recurring decimals. Okay, so recurring decimals are decimals where one particular digit or a group of digit will keep on repeating. Integers are represented by the letter z. Negative integers, so integers consists of negative integers, whole numbers, and natural numbers. So whole numbers are denoted by the letter w, whereas natural numbers are denoted by the letter n. Now in this slide we'll look at the properties of rational numbers. So first property is closure. So operation between two rational numbers like addition, subtraction, multiplication will always yield a rational number. Here is an example. So adding 1 by 4 with 2 by 3 results in 11 by 12. So all of them are rational numbers. Commutative property: the order of the number does not change result for addition and multiplication. So here we have, first we are multiplying 2 by 5 to 3 by 7, and then we are multiplying 3 by 7 to 2 by 5. Whichever way we multiply, the result will always be 6 by 35, and same is for addition. Next is associative property. So grouping of the numbers does not alter addition or multiplication outcomes. So let's look at the example given. So first we are adding 1 by 2 to 1 by 3, and the result we are adding to 1 by 4, and that should be exactly equal to if we are adding first 1 by 3 to 1 by 4 and then adding 1 by 2. Next is distributive property. So multiplication distributes smoothly over addition and subtraction. So here half is being multiplied to 2 by 3 plus 1 by 4. So these are in the brackets. So half will be first multiplied with 2 by 3, and then half will be multiplied with 1 by 4, as we see here. And the last property that we'll be discussing would be identity. So additive identity is 0. So when you add 0 to a rational number, you get the same rational number. And multiplicative identity is 1. So when you multiply any rational number with 1, you get back the same rational number. So minus 5 by 9 plus 0 gives me minus 5 by 9, and minus 5 by 9 multiplied by 1 also gives me minus 5 by 9. Next we'll look at the denseness property. So between any two distinct rational numbers a and b, there exists infinitely many rational numbers. So we can find them by the mean method formula. So a rational number exactly midway between a and b is given by the mean a plus b by 2. So here we have an example. So inserting one rational number between 1 by 3 and 1 by 2. So we'll add first 1 by 3 with 1 by 2. So the result is 5 by 6, and then because there are two numbers, so we'll divide the sum by 2. So the half of the sum is 5 by 12. So 5 by 12 lies between 1 by 3 and 1 by 2. Now we will look at how rational numbers are plotted on the number line. So we'll be plotting, the first number we'll be plotting would be 5 by 7. So the 5 by 7 lies between 0 and 1, and because the denominator is 7, that space between 0 and 1 will be divided into 7 equal parts. So there are 7 equal parts, as you can see, and out of those 7 parts will mark the fifth division from 0. So 1, 2, so 1, 2, 3, 4 and 5th. So here is our number 5 by 7. Next example we'll be looking at is a negative mixed fraction, which is minus 8 3 by 5. So that number minus 8 3 by 5 lies between minus 8 and 9. Okay, so we'll divide the space between minus 8 and 9 into 5 equal parts, because the denominator is 5, and from those 5 parts we will count 3 steps left from minus 8. So 1, 2 and 3. So here is our number minus 8 3 by 5. Now we will look at how to compare two rational numbers to find out which one is greater and which one is lesser, or if they are equal. So here I have a by b versus c by d. So how do I compare? So I'll cross multiply. So this method is called the cross multiplication method. So a gets multiplied by d and b gets multiplied by c. So here we have an example. So whether 4 by 7 is greater than, less than or equal to 5 by 9. So first we'll cross multiply. So 4 into 9 gives me 36, and 5 into 7 gives me 35. So clearly 36 is greater than 35. So 4 by 7 will be greater than 5 by 9. Now we'll come to the concept of terminating and recurring decimals. So terminating decimals, the decimal expansion ends after finite number of digits. So let's look at half. 1 by 2 is basically 0.5. 3 by 8, if you divide, you will find out that it is 0.375. Similarly 7 by 20 is 0.3 by 5. And the recurring or repeating decimals would be the digits repeat endlessly in a fixed pattern after the decimal point. For example, 1 by 3 is 0.3333, where the 3 is recurring. Similarly, 1 by 6 will be 0.16666, and the 6 will keep on repeating. So how do we express them? So there are two notations, bar notation and dot notation. So because in 0.3333 the 3 is rotating, we can either put a dot or we can put a bar over 3. So we can write like, it's shown already here. So either you write it like this or you write it like this. So either you put a bar or you put a dot. Now suppose a series of numbers are repeating. So this is 1 by 7. So 1 by 7 is 0.1428571,42857. So we can see that 142857 is repeating. So what we do is we put a bar over these numbers 142857, or what we can do is we can put a dot over the first number 1 and the last number 7. Both are correct methods of denoting repeating or recurring decimals. Now we'll look at how to express 2 by 7, 3 by 7 if we know the value of 1 by 7. So clearly in the last slide we have seen the value of 1 by 7 is that 142857 recurs after the decimal point. So notice the 6 repeating digits in order 1, 4, 2, 8, 5 and 7. So all multiples of 1 by 7 follows this exact same cyclic order. So let's take the example of 2 by 7. So starts at the second smallest digit 2. So in this series of number the second smallest digit is 2. So it will start from 2 and continue. So it will be, so 2 by 7 will be 0.285714. Similarly 3 by 7 will start from the third smallest digit. So the third smallest digit is 4. So it will start from here and go on. So 3 by 7 will be 0.428571. Similarly we can find out 4 by 7, 5 by 7 and 6 by 7. Okay. In this slide we'll look at the prime factor rule. So the prime factorization theorem states that a rational number p by q in simplest form has a terminating decimal if and only if the prime factors of the denominator q are of the form 2 to the power of m multiplied by 5 to the power of n, where m and n are greater than or equal to 0. Let's look at an example. So here the denominator is 8. So the denominator is equal to 8. So 8 can be written as 2 to the power of 3 multiplied by 5 to the power of 0. We know that anything raised to the power of 0 is 1. So this is of the form 2 to the power of m multiplied by 5 to the power of n. In the next case the number is 9 by 20. So 20 is 4 into 5. So which can be written as 2 square into 5 to the power of 1. So because this is of the form of 2 to the power of m multiplied by 5 to the power of n, this also has a terminating decimal representation. In case of 25, we can write 25 as 2 to the power of 0 into 5 to the power of 2. So this also has the form of 2 to the power of m into 5 to the power of n. So 13 by 25 also has a terminating decimal representation, which is 0.52. But let's look at the next problem, which is 7 by 30. So if you prime factorize 30, you will get it as 2 into 3 into 5. Now because there is another prime number 3 apart from 2 and 5, this will not be a terminating decimal representation, but rather it will be a recurring decimal representation. So the value of 7 by 30 is 0.2333, where the 3 is recurring. So we come to the end of the presentation. I hope you have understood the basics of rational numbers. So please feel free to subscribe to my YouTube channel or join the Facebook community. Thank you.